Okay, and now I'm delighted to invite on stage our next customer key opinion leader speaker, Professor Rafi Ahmed from the University of Inland, Norway. Rafi?
So thank you so much for the kind invitation. It's great to be back in Stockholm. I used to live here several years ago. I used to work for AstraZeneca and Medivir, so it's great to be back. And both my kids actually are born here at the Karolinska, so it's a lot of closeness to Stockholm. Okay, so I will talk about clinical metagenomics and how do we use it in infection and antimicrobial resistance. So my main affiliation is at the University of Inland, Norway, but I also have Professor 2, where Arctic Zymes is situated in Tromsø. And I am also a visiting professor at University of Southampton in the UK. Because I teach, so I thought, giving some basic primers on what is sequencing. So sequencing is when you try to find the number of nucleotides or building blocks for DNA and how many of those are present. For example, in a human cell, there are 3 billion of such A, T, G, and Cs, basically. And when you're trying to get the precise order of this is what is DNA sequencing. A lot of time, the word genomics and metagenomics have been used today. And I just want to make the difference. So if, for example, I am sequencing myself, one particular individual, that is genomics. If I take some cells from my skin or from saliva that has both my DNA and all the microbes that are in there, that is called metagenomics. So basically, you're trying to study DNA from a diverse microbial communities. And sequencing is not the main challenge. The main challenge is the analysis. I gave a talk at the Ahmed, which is a big clinical microbiology conference. Around 25,000 people attend the Ahmed. And the biggest challenge that they show up in metagenomics actually is bioinformatics and host depletion that we'll talk about. So there are several projects that we're working with, but the first result that I will talk about is from a project that's funded by Norges Forskningsråd, or the Research Council of Norway, and has several partners from Norway, Germany, and I'm originally from India, several of the top institutes from India that are involved. I'm really, really happy that we also have the key opinion leaders and the key policymakers when it comes to urology, the European Association of Urology, and I was really, really proud when the WHO became a partner in the project. So, and it's on urinary tract infections. So urinary tract infections are one of the most common infections worldwide, affecting 400 million cases every year. Out of this, around 20 to 30% of cases are recurrent. So you mean the patient has it several times. And it leads to around 240,000 deaths every year. There's an increase in resistance, so there's an increase in use of antibiotics in these pathogens. And the annual emergency care cost for urinary tract infections or complicated UTIs is around 3.5 billion. And this is especially the case in those who are immunocompromised, those who are on catheters, pregnant women, and so on. The standard care, it's culture urine, which was developed maybe 150 years ago. It is still the one that is used today, with a low detection rate of 30 to 60%, a lot of high false positive. And a lot of these tests are inconclusive, that leads to poor patient outcomes and longer days in the hospital. So this is a group of people that I've been working with. This is my team in Hamar, which is close to Oslo. We are really proud. Florian is one of the world's top urologists at the University Hospital in Gießen, close to Frankfurt. His team, and then Professor Truls Johansen, who got me to meet Florian, representing the European Association of Urology. So what we did is a 2-phase study, and Paul showed the first paper that we got out earlier this year. So in the first phase, we tested several different methods on 78 patient samples and compared our results. So we tested actually 8 of our methods, 3 commercial, and compared with what was happening in the clinical routine on 78 patient samples. This was published earlier this year in Nature Communications. Last time I looked at it, yesterday, it's already downloaded 10,000 times in a month of its release. It has an ultramic factor of 81, which is kind of unheard of. It's got a lot of popularity in the Norwegian media and the world media. We have a second paper that I submitted a couple of weeks ago. This number actually is incorrect. It's now 351, so we at least tested it on 351 patient samples when it was submitted. And I came to know last week that it has also gone to review. So you submit a paper to Nature, but it's not guaranteed that they actually send it for review. So this has also gone for review. So nearly 400 patient samples in total that we have tested the method. We have been talking about why host depletion is needed, and I just wanted to show the reason why it is needed. So if we take the example of urines, urine or most biological fluid has a lot more human DNA than bacterial DNA, right? They outnumber, if there's one cell of bacteria, there can be thousands of human cells. And you're trying to find those one human bacterial cells. In addition, urine is pretty complicated because it contains a lot of other immune cells, debris crystals, it has urea and so on, which makes extraction of DNA a bit complicated. So urine samples, and especially those that have urinary tract infections, have a lot of immunological cells, really a lot of blood sometimes. That makes it really complicated. So it is like finding needle in a haystack, but in this case, the haystack can be several different types of hays because there's so many different types of cells that are present. And that is where the host depletion and the SAN enzymes have been really, really useful for us. Yes. So I just wanted to show some science, not to go into the detail and say where we are actually using the host endonucleases. So when you get a sample, what you're trying to do is to reduce the number of human cells and increase the relative number of bacterial cells. So let's say you have 1,000 cells and there are only 10 human cells. Sorry, 10 bacterial cells and 990 human cells. What you try to do is reduce that number of 990 to, let's say, 90. And your bacterial 10 cells remain the same. That's what you're trying to do. So we tested both the HL-SAN and the M-SAN enzymes from Arcticzymes. And then when we had that, we basically did some lysis of the sample and then did some purification with magnetic beads. I'm really proud to say that this method is completely Norwegian because both the enzymes and the magnetic beads that we're using is all from Norway and developed in Norway. Tested in Germany currently, but it's completely developed in Norway. That's we should be very proud of because it's not that much innovation that comes from Norway. So what we did, basically, is we tested 11 different methods, and 8 which were in-house, and 3 that are commercially available, kits that are available to detect DNA or extract DNA. And the best method that we found was a combination of the M-SAN and some magnetic beads that are produced in Trondheim. Apologies for this complicated slide, but I'll just try to explain it. So what I'm trying to show here is how our method that is circled in this orange or yellow here, and how it is comparing to 2 other commercial kits that are available in the market. So when we are trying to see is that our method is depleting nearly 1,000-fold better than the commercial kits for the host, whereas the bacteria is not getting depleted. So that is what we wanted to achieve. You want to reduce the number of bacterial cells and DNA, but you don't want to deplete the number of bacteria. We achieved an accuracy of, actually, I'm presenting this next week in London, so I thought I can use the same slides at the European Association of Urology conference, which is like 15, 20,000 people come, and we are getting an accuracy of 99% when identifying which actual pathogen it is. This is actually the easy part. The difficult part is, can we say from the same method which antibiotic has to be used? Because if you go to a clinician, they're only interested to know, or mostly interested to know, which antibiotic can be given, and that's the complicated part. And even there, we are able to reach 92% accuracy. We're using a lot of machine learning here. So we are trying to identify the antibiotic from the metagenomic data. So a lot of machine learning approaches are going into our methods. And in most of the antibiotics, we are doing quite well. But there are certain classes of antibiotics like distrimethoprim we are trying to improve. The idea is to bring it as close to 99, 100%. I don't think it will ever be 100%, but as close to 100% as possible. We are already there with and that's where a lot of interest has been shown, even from the people in the UK, because our AST predictions are very good. Just to summarize, so currently, when a patient has urinary tract infections, comparing taking urine and the current methodology, it takes somewhere between 3 to 4 days in the best case scenario to tell which antibiotic has to be used. The method that we have developed actually has reduced it from 48 hours to 4 hours. That's a huge breakthrough in detection and treatment of complicated urinary tract infections, reducing it, because this can save lives, this can save lesser hospital days, lesser use of antibiotics, cheaper antibiotics, lesser days of productivity losses. Cost, one thing that I really fought for the Nature review was to put the cost in the paper, because as scientists, we don't like cost, but I wanted the cost to be there. So just to show that these two are commercial kits, that this is cost per sample. So we had a cheaper cost per sample. The most of the cost that is coming is actually coming from the sequencing. But the cost to extract the DNA with the SAN enzymes and the magnetic beads is actually only $6. It is a sequencing cost that is adding $30 to this. And we have some other ways on how we are trying to do as well. I mean, the other question is, do you really need to sequence everything? I did not want it to go into that, but that's in the paper. So, so conclusion of at least the first work, that this is from culture. So we're not culturing anything, we're taking the urine sample directly and giving the answer. This can help save millions of lives, reduce healthcare burden, fewer hospital stays, fewer loss of work days, and prudent use of antibiotics can save 1.6 billion doses every year. We have some other methods that I mentioned, but I've not gone into that, which says that, do you actually need to sequence everything? Your DNA isolation can already give you a very good idea whether there is infection or not. We have taken it further. We have a study ongoing at University Sykehus Norge. We are currently doing, from Sykehus in Landa, we get samples twice a week, which is just across the street from us. We recently, with help from the Karolinska Institute, we have set up a collaboration with the University of Turku, where we are getting samples from Finland. I'm really, really proud. Only last week, the first MSAN vials was sent to Delhi, and they were received in Delhi. So we are starting a clinical study at the All India Institute of Medical Sciences. Those who don't know, All India Institute of Medical Sciences is a premier hospital in India, catering to 20,000 OPD patients every day. Every day. If Modi is sick, that's where he goes. University of Hospital of Southampton, and then, like I said, really proud that the WHO is a partner which can help take it further. I also wanted to show a little bit of the work that we are doing on sepsis, which I think is where the biggest market will be, because that's where the biggest burden is. Again, funded by Norges Forskningsråd. It was a bilateral Norway-India project. Some of the people who have been working on this. So sepsis is time critical. 11 million deaths every year. 1 in 5 deaths across the world are because of sepsis. Like I said, time is critical. So with every delayed hour, there is every hour of delay in treatment, there's an increase in likelihood of death by 8%. Even in Norway, we have sepsis deaths. And diagnostics is one of the most important factors that leads to it. Sepsis is a huge economic burden. It's the #1 cost of hospitalization in the US, consuming more than 26 billion each year. Average cost per hospital days is also much longer, and readmission costs are also a lot because of sepsis. If you thought urine was easy, and I was interviewed by both Aftenposten and Narco, and I told them the same thing. If somebody is able to do sequencing from blood, it's a Nobel Prize. It's as complicated as that. So we recently started a study, again, with the Universitetssykehuset Nord-Norge in Tromsø, which is like 100 meters from where the Arctic Zyme office is, maybe 200 meters from where the Arctic Zyme office is. So we got 152 patient samples. And here, one thing that I wanted to say, that which SAN enzyme we are using is very much dependent on the biological fluid that we want to use. And here, we are not using the M-SAN, we are using the HL-SAN. We have tested both of them, but in blood, HL-SAN seems to work best. This is not yet published. We are still analyzing this work. But I just have some results which shows that we are actually getting 100% accuracy on blood cultures when doing clinical metagenomics compared to what is in the clinical routine. We are getting nearly 94% accuracy when trying to get which antibiotic is working. So it's working quite well, but again, this is not yet published. The results are being still analyzed. So this work has now gained a lot of attention. I wanted to show a video of the interview that I had with Anarco few weeks back maybe, but I just wanted to show that it has gone a lot of interest in the Norwegian media, saying that how Norwegian developed method can be really, really useful and spread across the world. I'm not into economics, but I just wanted to show a little bit about the global metagenomics. But what I really wanted to show that, although US is the biggest market, but I think some of the fastest growing markets are actually in Asia. Because that's where the burden to the society on infection really is. And there, I think there's more openness to take up new methods. I think in Europe, we are still a bit conservative. The key takeaways, this has already been said, but clinical metagenomics can be applied to several different fields like cancer, but the primary driver currently is infectious diseases, actually. And falling sequencing costs. I don't know whether any one of you have seen Oxford Nanopore device, but it is smaller than my mobile phone, actually. I can take it to the bedside and sequence a patient if I want to. So, and one of the biggest bottleneck is bioinformatics and regulatory frameworks, obviously, because we don't have current standards, current frameworks, but bioinformatics is the challenge currently in clinical metagenomics. So that was my last slide. Thank you so much.
Any questions?
Okay, thanks for a great presentation. Ludwig here from Nordea again. Continuing a bit on what Lee said before, I think he mentioned or described very clearly why M-SAN was outperforming other nucleases in their protocols, which was mainly due to pH and salt levels and so on. So in the metagenomics field, is there a similar reason why M-SAN outperforms in here? Do you also need to have the samples in very specific, types of pH ranges and so on?
Yeah, so so for example, in urine, M-SAN is what we tested both M-SAN and HL-SAN. and M-SAN works slightly better than HL-SAN for urine. But for blood, HL-SAN works better. And there are different reasons, because urine has a large range of the pH, both from alkaline and can go so acidic to alkaline. Blood is a little bit more alkaline. So it depends a lot. We are also working on some other body fluids, which I cannot mention. And there also we see that you cannot say it's only M-SAN. In certain cases, HL-SAN also works. So it's very much dependent on the characteristics of the sample that you're working with.
Okay, and I guess, just like somewhat of a follow-up, but now I forgot what I was going to say. So I jumped to the next one. Just thinking more broadly then on using these types of work protocols or workflows in hospitals. So I guess 92% accuracy does not really make it a direct replacement for cell culture, where you probably need a bit higher, I guess, accuracy to ensure that you use the right antibiotics and so on. So how do you view, how should hospitals use this in the future?
So FDA allows for greater than 90% actually. And cell culture, I did not go into the depth, but through metagenomics, we were also able to identify pathogens that cell culture did not identify. And we validated them with a PCR afterwards. So because it is an agnostic method, it can give you whatever there is. So it can help you identify those infections with normal cell culture would not be able to identify. And I can go into much detail, like there are a lot of bacteria that go very slowly, and that can days, weeks. But in metagenomics, because you're not doing any culture, you can identify them much more faster. I think one of the bottlenecks currently is the AST, 92, 93% that we are in. So the more data that we will get in metagenomics, the better our machine learning algorithms will become. And that will actually improve also the prediction of which antibiotic will have to be given.
Yes. So in the long term, then I guess it could replace what you use today in hospitals.
Yes, I get asked this question quite a lot, and I would say I don't know the time frame, but I would say probably around 5 years or so. Our next step, we're going to the Regional Etikkommittén for approval now to test them, because I get asked this question quite a lot also, that, okay, the method works very well in your labs, how will it work in the lab? In hospitals, that's our next thing. But I think I wanted to say that if it works in Delhi, I think it will work anywhere in the world.
Okay, great. Now I remember what I was going to ask before, just on the first question. So, like, what I guess I was going for was, like, why would M-SAN or SAN outperform a nuclease, like a more general nuclease that you could buy from other players? Is it due to these pH levels?
Salt is another one. I think mentioned that we tested some other nucleases in but it is a salt, a wide salt range, because the salt concentration in body fluids is quite high, and a lot of the other nucleases cannot tolerate that.
Okay, so it's basically a more versatile nuclease in that sense. Okay, great, thanks.
Hi, Phil from Pareto. So first, and sorry if I'm getting into too many details here, but you mentioned in the end there that bioinformatics is a major barrier here, or bottleneck. So I was just wondering, is that, like, if you could go into some more details around how that is? Is it because you're using nanopore and you get real-time data, or is it around the complexity of the sample mostly, or,
Yeah, I mean, there are basically several reasons. One of the first reasons is as simple as that most people in healthcare, like nurses, doctors, they are, when it comes to using technology, it's not that easy. So there's more effort needs to be done in easy-to-use bioinformatics tools. First thing, as simple as that, a graphic user interface kind of things. The other thing, obviously, is because there are still errors in your sequencing, right? And because of that, between some of the reasons why we are not able to get 100% AST is because one single nucleotide change can cause a different antibiotic to be used. So that is thing. So, but nanopore has worked quite a lot, so now the accuracy is still quite high. But this will improve. The other thing is we don't currently have standards to report, right? Do we report everything that we find? Because metagenomics, like I said, will find everything. But not every bacteria is pathogenic, right? So these set of standards are still not established. So that is the other thing. But the biggest challenge is, another one is good, reliable, easy to use bioinformatics pipelines are not yet there. In our group, we work a lot also on developing bioinformatics pipelines. So that is, I think, is one of the biggest challenges currently.
Okay, and would you say that's one of the biggest barriers into actual clinical adoption then?
Absolutely.
Just get that. Okay,
absolutely. And this is not only me saying, this is in these reports, and I presented at Ahmed in Barcelona. Ahmed has 25,000 people attending it, and I had a question to the audience on metagenomics, that do they think metagenomics will be in clinical use? And 90% people said yes. My second question was, what they thought was the biggest bottleneck? And I thought people will say that it was resistance to uptake of new technology, but 2/3 of the people say bioinformatics. So this is
very, very interesting. Perhaps second question is then on the cost savings here. You said goes from 96 hours to 4 hours. So just that fact seems to have the potential for massive cost savings for the hospital. And you mentioned that it costs $36 for a test, but that seems to be nothing in comparison to the overall cost savings that could be achieved. So if you could just give some comment around this.
Yeah, I mean, to us, it looks like a no-brainer, right? That you're bringing down your cost because 96 hours, you save a lot of other things, lesser hospital days, right? Lesser people involved. But one of our challenge now is talking to the communal helsesjenester in Norway, right? And trying to convince them, because when they think about the cost, they only compare the cost of the diagnostic method to the current diagnostic method. So for us, the next challenge is to overcome that hurdle and tell them it is not only that cost, it is a lot of the other costs that are associated. So that is, I think, more of a personal communication challenge than anything else. But we are in dialogue both with the Inlandsfylkes commune and Hamar commune to test it within our fylke.
Okay, thank you.
I think to add into that, and we talked about it earlier, is that there's definitely an element of surveillance. So there's this clinical application where clearly you're looking to manage an individual patient's pathway. But if you look at the UK, two of the strategies are specifically designed around pandemic surveillance and around antibiotic resistance surveillance. So this is where that conceptual leap has been made. They've moved past this and they're looking at the wider societal costs, which is why it's being funded. It isn't simply being driven by hospital economics, where there is a very strong argument, but it's actually a wider community element where you're looking at how you manage antibiotics across your country, how you manage your surveillance. So it is bigger than that.
Absolutely, yes.
Okay, I think we're at time. Thank you very much, Rafi. It's appreciated. I'm now going to hand over to Børge.